This is all about building physics, and designing buildings with confidence requires accurate knowledge of building thermal properties. But how can we assess whether thermal transmittance values are equal or higher than those in manufacturer's specifications? That is always a very good question. And we can do that by physical tests, which can be like a co-heating test or a dynamic heating test. This study replaces the need for physical tests with actual buildings. And in the first stage, we're going to look at simulated tests with calibrated models. In the second stage, we're going to look at machine learning. So I did physical tests in buildings and found that you can actually achieve these exponential curves when you switch the heating on, you switch electrical heaters on, and this was meant to actually calculate overall heat loss factor, but heat loss coefficient. But what I realized during this investigation is that you can actually calculate dynamics of building performance by fitting a curve to the measured value, and then finding out the time constant, which is the time that it takes, it takes for a building to go through 63% of the total change from when you apply the heat. And from that you can calculate also the heat loss coefficient when the building goes into steady state in the end of that curve, and then you can calculate the thermal capacitance. So you get three values from the same test. Now, physical tests are invasive because you cannot have people inside the building. And there are internal cracks that appear from heating to higher temperatures. I was heating this house to 50 degrees, and there are internal cracks happening. But what happens when you actually have people living in a building through retrofit process? So we have on the left a building before retrofit, and on the right after retrofit. So what we did, we calibrated the simulation model. We used multi-objective optimization, where we varied wall construction types and roof types and window constructions, infiltration rates, heating set temperatures, and also lighting power density and miscellaneous gains power density, and got an optimal model. So that model was then subjected to a dynamic heating test. And as a result of that, as a result of the calibration of the model, we got accuracy of the model in excess of 99% in respect of heating energy and electricity energy consumption. So we subjected that model to dynamic heating tests. And you can see here tests with 3 kilowatts, 6 kilowatts, and 9 kilowatts. And we then fitted the curves to these test results. And this is considered to be like measurement, because the calibrated model is a result of measurement. We compared the results of dynamic heating tests, simulated tests, with theoretical heat loss coefficient values, and found that there are quite significant differences. You can see after retrofit there's 97.89 watts per Kelvin heat loss coefficient, and it's 147 plus minus 12.52. So when you unpack this, you take mean value plus standard deviation, or mean value minus standard deviation. I'm just trying to point here, but the pointer doesn't seem to work. You get the values, discrepancies between existing theoretical values and measured values of more than 60%. This is when alarm bells start ringing, because these are theoretical values that we use to design buildings, but they're significantly different. So the simulated dynamic heating test is not invasive. It uses continuous monitoring as source of data. It still requires human intervention. But is one-time test sufficient for the entire year of the lifetime of the building? And can building physics properties be obtained through self-organized simulation? So if we look at theoretical influence of external temperature on the internal temperature, if we say external temperature is a sine function and internal temperature is also a sine function, but it's time delayed and attenuated. So you would think that this is going to happen in reality with real data. If we plot these two sine functions one against the other, we get a nice elliptical curve. So we have internal temperature as a function of external temperature. So surely, if building physics properties are constant, we should get the same for measured data. However, we don't get the same for measured data. We get completely erratic performance when we plot internal temperature against external temperature, which makes me think that building physics properties do appear to change with time, maybe because of moisture content, maybe because of something else. Therefore, one-time tests are not sufficient for a complete knowledge of building physics properties. And how can we then achieve continuous learning of building physics for a control system? Can a self-organized model be developed using machine learning? And can such model measure building physics properties in a control system without human intervention? We investigated 3 different methods: exhaustive search, random search, and genetic algorithm search. So we're trying to find heat loss coefficient and time constant for the building. In exhaustive search, we had to have 2 nested loops, double nested loop for heat loss coefficient and time constant, and that gives algorithmic complexity of n squared. And if we take, for example, something like 4,500 possibilities for heat loss coefficient and 700 possibilities for time constant, we get more than 3 million combinations to do in one time step for learning. That's too much. Exhaustive search is similar complexity, but it doesn't happen all the time, so it can be simpler than that, but it is still uncertain whether it's going to give results. The genetic algorithm is n log n complexity, which means for 100 generations we get something like 200 calculations, which is pretty reasonable for the algorithmic complexity. So we had a machine learning model developed for this purpose. We had a population of 100 chromosomes. Each chromosome was combined from heat loss coefficient and time constant. We converted these numbers into hexadecimal numbers and then combined them as strings. And fitness of each chromosome was calculated using root mean square error. What was happening then, we, according to the root mean square error, we sorted these chromosomes. We took the most accurate ones, applied crossover and mutation in terms of genetic operations, and also transferred small number of existing of the unmodified chromosomes into the next generation. And we did that for several different sets of genetic algorithm parameters, so that, for instance, we had parameters for cross-generation of 80, 60, 40, and 20 out of 100, mutation 5 to 10 out of 100, and all generation from 15 to 75 out of 100. And we found that, again, there are differences between existing theoretical heat loss coefficients and heat loss coefficients calculated by machine learning. Discrepancies are still quite high, in excess of 30%. So you can see here the results of simulations under 3 different sets of power inputs, heating inputs of 3 kilowatts, 6 kilowatts, and 9 kilowatts for each one of these sets of genetic algorithm parameters. And so when compared with the theoretical values, we are having differences from something like 27% to about 32%. Considering that there is a degree of randomness in genetic algorithm operation, so for example, you first create a population at random using the chromosomes. We wanted to see whether this randomness affects the results. So we did simulations or calculations of 10,000 different runs. So these are effectively 10,000 runs summarized in one chart. The results for heat loss coefficient and for the time constant are all ranked. They are all ordered so that we see how they go from low to high. And there is a difference of about 35 watts per Kelvin between high and low for heat loss coefficient, and very small difference in hours for time constant. And these are the errors, root mean squared errors for heat loss coefficient going from 120 to about 135, almost 140. So very low heat loss, very low root mean squared errors. For that reason, we managed to implement this machine learning in a predictive control system, and that operates without making the control system non-responsive. It's very fast to learn. It learns once a day, and this actually now controls my house, so I'm the guinea pig here, learning how it works and then deploying it elsewhere. But machine learning therefore enables self-organized simulation model to be developed, and continuous learning replaces the need for separate model calibration. There is low algorithmic complexity of n log n, and the algorithm operates without making the control system non-responsive. In conclusions, I presented method development for measuring building physics properties. Analysis of physical tests provided suitable equations and development of simulated tests. Simulated tests provided non-invasive solution to building physics measurement with calibrated models, and machine learning replaces the need for model calibration and enables self-organized simulation. The methods introduced here are tools for establishing physics properties of buildings in use. And this facilitates quality control of retrofitted projects. So if you want to investigate whether your project has the same U values as you envisaged, you need to check that with this kind of test. And self-organized simulation is suitable for continuous learning and operation on a control system. There are significant discrepancies between theoretical and measured heat loss coefficient values, and building physical properties need to be established for the existing building stock before deep energy retrofit. And there's an urgent need for a review of technical reference tables and I guess standards as well. And safety margins need to be implemented when designing, considering discrepancies of up to 60% of heat loss coefficients between theoretical and measured values. Thank you for listening, and are there any questions?
Fantastic.